Hello, everyone, and welcome to another live session for our online course. The floor is open for any question in astronomy. I assume I can answer. I'll do my best.
Okay, what's the biggest challenge for cosmology today?
Given the overall success of the hot Big Bang model with lots of evidence to support it, and pretty good measurements of the age and current expansion rate of the universe, the biggest challenge clearly is dark matter and dark energy taken as a pair. But in a sense, dark matter, there's a fair amount of progress and also a fair amount of data and information on where it is, how it's distributed, and by process of elimination, things that dark matter cannot be explained by. So in those terms, the biggest challenge to cosmology is clearly dark energy. And that's because dark energy is the biggest challenge to physics. It represents new physics. If it's something that causes the universe to accelerate and is its expansion, then it's presumably a property of the vacuum. And while physics does attribute vacuum energy to the vacuum, that's a part of quantum theory, if you go through the calculations, the impact of quantum level dark energy on expanding space-time is completely inadequate to explain the expanding universe. Actually, if you go through the calculation, the quantum level force, repulsive force, would be far too large to explain the accelerating expansion. So physics provides essentially no insight, standard physics, quite successful standard model of particle physics, no insight into dark energy, and astronomers equally have very little clue as to what dark energy is, because the main symptom of it is the accelerating expansion of the universe, an observation now 20 years old that has been confirmed and corroborated. But as far as getting additional information on what dark energy is, astronomers have mostly come up blank, although there are signs that dark energy does not vary over time and space. That's about it. So it acts like Einstein's famous cosmological constant. So this is probably at the level of a crisis. I think physicists even consider it a crisis, the question of dark energy. And for astronomy, it's just a huge puzzle.
All right, the next question is from Lori, who is on live with us right now. Can you explain how gravitational energy is changed into magnetic radiation or light through fusion? So basically, can you explain fusion and the relationship between the different forms of matter and energy?
It's an important part of basic astronomy, that stars, to put it simply, are gravitational engines. Because a star is formed by gravity, it's the concentration of matter that was very diffusely distributed when a star forms. So the material that ended up, say, in the sun was originally distributed over a much larger area, and its density correspondingly increased when it collapsed. Then, however, being held together by gravity, the gravity energy, the gravity potential energy, is the engine that drives the star, because that energy is sufficient to keep an internal temperature high enough for fusion to operate. So once the star stabilizes in its fusion reaction state, the star is in balance, where the gravitational inward pull at every point is balanced by radiation pressure from fusion reactions in the interior. And that's why stars are stable, and they're not really analogous to bombs at all. But again, the entire cause of a star's lifetime emitting electromagnetic radiation is gravitational potential energy. So gravity energy powers stars and continues to do so until they run out of their nuclear fuel. At some point in the star's life, the fuel source is exhausted, in the sun's case, because the sun's not massive really to go up the higher stages of fusion, so the sun will create a lot of helium and a little amount of carbon, and then that's the end of the road for the sun. However, the gravitational energy remains. The star is about the same mass. The gravitational potential energy is the same. So gravity is the winner in this battle. And in the ultimate states of stars, white dwarfs, neutron stars, and black holes, we see the victory of gravity.
All right, the next question is from Alice Amanda, who would like to know if you know what a Hernquist sphere is.
It's hard. This is like the Cartog guy stumped the chump. No, you've stumped me. I don't know what a Hernquist sphere is. I'll have to go and look it up. If you have time, if you're on live and can go off and explain to me what it is, I'm sure I can provide some elaboration. But the terminology, I simply don't know.
All right, the next question is, From the same person, they would like to know if you have any thoughts on the bright spots on Ceres.
Sure. Well, planetary scientists are still puzzled over that one. The best guess is, of course, that those are icy regions, very highly reflective, almost perfectly reflective, like glass. And also, as with the case of Pluto, with its strange landscape that appears to have been resurfaced, it's also likely that such bright regions, so different from the rest of Ceres, represent a place where there's extra energy. So they're probably, ironically, although they look icy, they could also be hot spots, which means they could be places where water is bubbling up from below the surface, where it's kept under pressure by gravity, and then, of course, as soon as it reaches the surface, it will instantly freeze, and so that's why you would see an icy deposit. So the white spots seem to be ice, but they could represent internal heating in Ceres, which is very exciting because it's quite a small object and shouldn't have a lot of internal heating. But then again, neither should Pluto, because Pluto has resurfaced itself many times as recently as 100 million years ago, and it also should not have internal heating. So these are kind of big puzzles for planetary scientists.
Argon Moore over email would like to know, in the Hubble Deep Field, we see images of galaxies back to not long after the Big Bang, cosmologically speaking. Would it be possible to capture an image of our own galaxy when it was being formed in one of these deep field images as we look back in time billions of years?
So in some alternative universe where space was curved, where we lived in a closed, positively curved universe and light wrapped around the universe, then it's possible you could see your own galaxy with distant light. Basically the light just wraps around the universe, and so we look out and we can see ourselves when we were young, almost like a time travel trick. That would be exciting. But our universe is not like that. Our universe is flat space-time, so light from our galaxy just travels out into space and travels forever, never to return. And so that means we can never see our galaxy as it was when it was young. But we know what our galaxy is like now. We know that it's a spiral galaxy that formed from many different pieces, from mergers and accretion of gas and small galaxies over time. And so while we can't see our own galaxy when it was young, in the Hubble Deep Field, we can identify many proto-spirals or spirals on their way to becoming our size galaxy after 11 billion years. And that's a game that astronomers play. Essentially, we use the Hubble Deep Field to identify counterparts to our old mature galaxy at different stages in their earlier evolution. Now, it's not perfectly reliable to do that, but it's a way that astronomers use the Hubble Deep Field to tell the story of galaxy evolution.
All right, the next question is from Stephen, who is on live. And Stephen asks, can you please compare and contrast the fields of astronomy, cosmology, and astrophysics?
Yes, the terminology sometimes can be confusing. The two that are essentially synonymous in academic terms are astronomy and astrophysics. If you look around the country, say, of university departments, you'll find some departments of astronomy. Well, first of all, you'll find many departments of physics where astronomy or astrophysics is just a group within the physics department, just like solid state physics or high energy physics or biophysics is a group. And there again, you'll find these more or less synonymous. You'll often find an astrophysics group in a physics department, but you might also find an astronomy group. So those two terms are slightly interchangeable. Now, some departments sort of hybridize them, and there are departments of astronomy and astrophysics out there. And the reason they would want both words is that the astronomy word is perhaps the more traditional word that connotes observing the sky and astronomical objects, whereas astrophysics very directly refers to the act of understanding how things work through the application of physics into the universe. So some people, some academics are a little pedantic on that, and they prefer astrophysics because it alludes much more directly to the physics backdrop with which we interpret astronomical observations. So those two words are used interchangeably, and some people have strong, almost irrational preferences for one or the other. I live in a department of astronomy, and our own graduate students, just as an aside, have lobbied us to change our PhD name from PhD in astronomy to PhD in astronomy and astrophysics, as many of our peer departments do. And they do that for the very sort of prosaic reason that they think it'll help them get jobs potentially in physics departments by having astrophysics in the title of their PhD as well as astronomy. Cosmology is just a subfield of astronomy or astrophysics. So cosmology is the subfield of the larger subject that relates to the study of the universe as a whole.
So Ravi over email asks if you can tell him your opinion on the role of computer science, including machine learning, in how we study and improve our understanding of the universe.
So that's a good question, because this relationship has changed and evolved quite a lot in the last few decades, and especially in the last decade. Computers have always been important in astronomy, really going back 100 years. There was a famous episode in pretty much 100 years ago in the 1920s and 30s. The Harvard College Observatory employed young women as what they called computers, and they were just manually by eye scanning photographic plates that had spectra on them and sometimes images, and they were manually digitizing them and transcribing the information or classifying those stars. Some people did, that tens of thousands of times. And those women, it was a not too happy period in the history of the subject in terms of equity. Those women were paid apparently 50 cents an hour back in the day, and of course less than guys would have been paid for the same thing. And they were called computers, and so there was no way to digitally scan and record information in astronomy then, and made astronomy pretty tedious then. You observe one object at a time, and with that level of data rate, you sort of didn't need computers anyway. Well, computers didn't really come out of the realm where they were the size of a large living room until the 1970s. And as soon as they did, as soon as the personal computer was developed in the 1980s, astronomers were using them to reduce their data. So in the parallel evolution of detectors to be digital detectors, CCDs, with large numbers of pixels, thereby recording megabytes and then gigabytes of data each time you open the shutter, take an image, and computers to process that information, those two things went hand in hand through the 80s and 90s, to the point where, of course, computers became integral in reducing data in astronomy. Now, that doesn't only use some of the sophisticated forms of computer science and machine learning that the questioner was alluding to, but that has started to come in too. So the other thing that's going on, apart from just using computers to reduce your data, is using computers to simulate astrophysical phenomena, whether it's the death of a star as a supernova or the gravitational structure that forms in the universe from smooth initial conditions. Computers now, and in the last 15 years, have been essential for that work. It's impossible to do it any other way. You can't calculate it by hand or with equations, even though equations apply to the microscopic details of it. To do it in the aggregate, you need computers. It's, again, not necessarily machine learning. It's more extremely clever algorithms developed by astrophysicists to do that type of calculation very efficiently and to parallelize it in the form of cosmological simulations. So you can do essentially billions of different gravity calculations over many different time steps very efficiently. Machine learning has been tried in terms of some projects like classifying galaxies. Galaxies, it turns out, have enough structure and similarity and regularity that machines can be used to classify them, but they also have enough quirks and peculiarities that machines don't actually do very well at it. So machine learning has been applied to a couple of fields in astronomy, like galaxy classification, not entirely with success yet. And I'm sure the algorithms are still developing. So it's a very fruitful area of research now. And most astronomy departments have obviously technical expertise. They often employ computer scientists, people with PhDs in computer science, sometimes even at higher levels than that. So they're very closely related now in modern research.
Okay, the next question is from Sana, who is on live with us. All matter was created in the Big Bang, where all matter was concentrated in a very tiny and dense point, but how can we say dense when there was no Higgs field, or was there in the very beginning, since it wasn't created yet? Was matter at first massless?
And that's a good question, and it relates to issues of the Big Bang that are currently subject to speculation and not understood. So that's the short answer. We simply don't know. The speculation about the Big Bang is that the mass was the mass of the universe, given the interchangeability of mass and energy by equals mc squared. The mass of the universe could well have originated from the vacuum of space, the so-called false vacuum state, where the universe, in a sort of quantum fluctuation sense, goes through a phase transition, and that's the false vacuum. And that energy essentially borrowed from the vacuum is sufficient to inflate super fast a small region of space-time, where the energy then floods into the space and is converted by equals mc squared into mass. All this happening in the first tiny fraction of a second after the Big Bang. The role of the Higgs field in that is that it is involved in that. Higgs is the mechanism by which mass is attributed to particles. But the Higgs field doesn't directly apply to this situation, because this is a situation when all the forces of nature are unified in a so-called superforce, whose nature we simply don't understand now. So Higgs field physics is not necessarily applying the way we understand it to this super dense, super hot state. And again, we need new types of physics to understand that.
All right, so the next question is from Lionel via email, and it's a two-part question, but they're related. So I'm going to flip the order, and the first question is, why does the elliptical orbit of the Earth not influence its seasons? And then to go along with that, what's the difference in a planet's orbit? Like, what's the sort of change in to be in the circumstellar habitable zone? Like, how far away from a star can a planet be to be habitable?
So it's a classic, of course, misconception in astronomy that instructors of astronomy have to deal with every semester, every time they teach, that most students, maybe not most, but a large fraction of students or members of the public who haven't taken an astronomy course, think that the seasons are caused by the elliptical orbit of the Earth. And I would say that impression is exacerbated by the fact that in textbooks or diagrams you'll find online, if you do Google image search, it looks highly squashed. So the perspective view of the Earth's orbit presents it as very elliptical, and that's just because in looking down on a nearly circular orbit, if you tilt your view, it starts to look like an ellipse. So the Earth's orbit is only 4% elliptical, so it's deviating by a circle by only a few percent. And if you do the math of that, then the effect it would have on the radiation of the Earth at its closest and furthest approach is, it's an inverse square law, of course, the radiation law. So you've got to just take 1.04 squared or 0.96 squared and see what extra amount of radiation that is. And you can, simple math says it's about 10% or less. So the Earth-Sun distance variation can only give you a relatively modest variation in heating from winter to summer. And then the other problem with that, of course, is that we know that the seasons are reversed in the northern and southern hemispheres. So if the whole Earth should get hotter in one part of its orbit and cooler in another part of its orbit, then the whole Earth should get hotter and cooler. And so there's no way our seasons should be the opposite of those in Australia and South Africa. So the rebuttal to the distance being the reason for the seasons is both that the effect is small, because the Earth is only very slightly a squashed circle, like a very slightly elliptical, and also because seasons are felt in opposite senses, northern and southern hemisphere, leading therefore to the correct explanation that the Earth's orbital tilt of 23.5 degrees is sufficient to create a large difference in apparent heating, because the angle of illumination of the sun varies by quite a lot. The difference, between the tilt going away from the sun and towards the sun is twice 23.5. That's 47 degrees. And if you made a little diagram of the Earth pouring straight in from overhead or being tilted at 45 degrees, you can see that the illumination pattern changes a lot, and the heating effect is more like 30 or 40%. So that's how we know the seasons are caused by the tilt of the orbit rather than variation in Earth-Sun distance. For habitable zone and nature of orbits and habitable zone, the ellipticity of the orbit does clearly play a role. If the Earth's orbit were highly elliptical, or any planet, then even if its average distance from the sun might keep it in the habitable zone, its extremes, close and far, might take it out or away, or in or away from the habitable zone. So if you had a highly elliptical orbit, your planet is simply less likely to be habitable, because while at the average distance water might be a liquid, you might have a situation where the water would boil when the planet is close and freeze when it's far out, and that would mean in a yearly cycle it would be pretty tough for life to keep going and develop and evolve under those extreme conditions. So habitable zone it's a good question, because habitable zone does not just imply average distance from a star of any planet that's sufficient for water to be liquid and the temperature of the surface to be temperate, like room temperature, but also that the orbit not be extreme, that the orbit not either have a large orbital tilt. Our orbital tilt, 23.5 degrees, is a sort of intermediate tilt. So if the orbital tilt was 45, 50, 60, 70 degrees, the seasons once again would be extreme, or too large in ellipticity, because then the distance between the near and the far points from the star would be such that habitability would be very unlikely. So planetary astronomers pay attention to both of those things when they try and define what habitability actually means.
Okay, the next question is from someone who is online with us. What is the diffuse intergalactic medium discovered by Hubble? I have never heard about it. Can you please throw a little light on that discovery?
So the intergalactic medium was hypothesized because we thought that the space between galaxies shouldn't be in an entire and perfect vacuum. Turns out the space between galaxies has an average density of about 1 particle, which would be a proton, so it's mostly hydrogen, per cubic meter. So you can compare that to the interstellar medium, that is space between stars. You go far from the sun towards the nearest star, somewhere in the middle between all the stars near the sun. The average density of that medium is maybe 1 or up to 10 particles per cubic centimeter. And so the density in the intergalactic medium is a million times roughly less dense than the interstellar medium. The interstellar medium is, of course, an almost perfect vacuum, a billion times less dense than the air we're breathing. So it's a difference between an incredibly good vacuum and an almost perfect vacuum. But that 1 atom per cubic meter, of course, adds up because the space is so large. So the space between galaxies, while fantastically low density, does amount to a fair amount of material. And the speculation went back into the 60s and 70s of how you would detect such a diffuse medium. So people hypothesized its existence, but just simply thought they couldn't be able to detect it. It was in the end detected in 2 quite different ways. The first way it was detected was in absorption, which is where light travels to us from a distant quasar, and essentially you don't care what a quasar is for this observation. It turns out it's a supermassive black hole, very large distance away from us. But for this observation, you treat it as a flashlight. It's just a flashlight a long way away across the universe, shining towards your telescope. You spread the light out into a spectrum. And it was observed back in the 60s, and it was a prediction actually from the early 60s, confirmed maybe by 1969-70 when spectrographs on 5-meter telescopes like at Mount Palomar got good enough, that the spectrum is chopped up by very narrow absorption lines. And those absorption lines represent hydrogen, H alpha, the hydrogen alpha line, in absorption, each line representing a different distance along the line of sight to the quasar. And when you do an analysis of the nature of the absorption lines, you can determine the physical state of the gas. And so the hydrogen strung out along this incredibly long one-dimensional sight line across the universe, you can do an inventory of it using these quasar absorption lines. And you can show that it's almost randomly distributed, doesn't cluster like galaxies, and therefore it is truly intergalactic. And then the second thing you can do by studying the ionization state of it, you can determine, and this was a surprise, that gas, that incredibly diffuse gas, the space between galaxies, is actually really hot. It's hundreds of thousands of Kelvin, up to about 1 million Kelvin. For a while, that was a kind of a surprise. Why would this incredibly diffuse gas in what is essentially frigid space, just with a temperature of 3 Kelvin, the microwave background temperature, why would it be so hot? And the answer is that the diffuse gas is heated by the aggregate of all the ultraviolet radiation of galaxies in the universe. And in early universe, and when galaxies first formed, there were a lot of young stars, a lot of ultraviolet radiation. That ultraviolet radiation eventually spreads out into space, intergalactic space, and it heats this very, very diffuse gas into a very, very diffuse plasma. So that is what the intergalactic medium is. It's a very, very diffuse plasma with a temperature of a few 100,000 Kelvin. And then much later, maybe only 10 or 15 years ago, people did the full inventory using now much better telescopes and spectroscopy of how much material is in that intergalactic medium. And that answer was an interesting result too, because it turns out that diffuse, very hot gas contains as many baryons, or normal particles, protons, neutrons, electrons, as all the material in all the stars in the universe. It actually contains maybe twice as much. So it's one of the biggest repositories of normal matter in the universe.
Okay, the next question is from someone else who is on live with us. And they would like to know, what are gyros? As mentioned in the video about Hubble, what does it mean that the gyros are failing on the Hubble telescope?
Gyroscopes are used, they've had a role in space and telecommunication and satellite industry for a long time. It's just a gyroscope. It's an abbreviation for a gyroscope, and you can, really think of it as just the little child's toy, a large spinning mass with a large angular momentum, in physics terms, a large moment of inertia, because it has mass distributed away from its rotation axis, so it holds a lot of angular momentum, and that stabilizes it about its spin axis. And its stabilization about its spin axis means that spin axis points very accurately in a particular direction, in whatever direction it was pointing when you spun up the gyroscope. So spacecraft are stabilized, all spacecraft, this goes back to the beginning of the space age 60 years ago, by very, very high quality precision gyroscopes. And in these cases, the gyroscopes are sealed, usually in a vacuum, so they're sealed units. They're spun up to high speed by power sources on the spacecraft, but because they're in a vacuum and they're lubricated or have almost no friction, they need almost no power to keep spinning. So those gyroscopes just keep spinning, and because of that, they keep pointing very stably at a direction. So spacecraft point using gyroscopes, and if you want to point in three directions, three spatial directions in space, then technically you need three working gyroscopes, each oriented 90 degrees from the other, or just at some angle between them that you can understand and calibrate. So most spacecraft, especially ones that point at different objects in the sky, like a telescope, will need three working gyroscopes to operate and to point the telescope and then move it to another object and know where it's pointed. And that's the case with Hubble, but it's also the case with all the other telescopes that are up in space. Hubble was obviously, the gyroscopes being essentially critical for its functioning, Hubble had a redundancy, and most of its systems had redundancy. So Hubble was built with 4 gyroscopes, and they were working right from day one, so that even if one died, it could keep functioning completely normally. If the second one dies and you're down to 2, there are clever methods to use what are called the fine guidance sensors, which is actually just one of the Hubble instruments, to sort of stand in for the third gyro. So Hubble could actually afford to lose 2 of its gyros and still function moderately well, almost to spec. But if Hubble ever loses 3 of its 4 gyros, it's dead in the water. Essentially, it can't really point. I mean, it can point, but it doesn't know where it's pointing, and it can't change direction. What happened was, after these gyroscopes, as a critical component of Hubble, they were tested on the ground. Extensive lab testing, of course, and even under vacuum and cosmic ray conditions to simulate space. And one of the puzzles of the Hubble project is that those gyroscopes never really failed. They performed exceptionally well. I don't know if there was maybe there was one failure of all the spare Hubble gyros that they kept spinning on the ground. But they never failed on the ground at the rate they ended up failing in orbit. And that was one of the puzzles of the project that I don't think they've still resolved. So what happened when Hubble was launched was that the Hubble started failing one every few years, pretty much randomly. They couldn't predict which gyro was going to fail and when it was going to fail. And that was no problem for most of the mission because every few years there was a Hubble servicing mission. So one of the things almost essentially all the Hubble servicing missions did was swap out gyroscopes. Initially, they only swapped out the gyroscope that might have died, the spare one, the one they didn't need. By the time of the last couple of servicing missions, they were so worried about the gyroscopes failing that they used the servicing mission to replace all of them, even the ones that weren't showing any sign of problem, because they simply didn't know when they'd fail. And Hubble got down at one point to that one gyro situation and actually had some downtime because of that. And indeed now, in its final phase, where Hubble's not going to be serviced anymore, that is likely the reason that Hubble will die. That its gyroscopes, which have been failing at a particular rate, but randomly, over the whole mission, eventually enough will fail. It currently has full complement, so it's not a problem right now. But if Hubble loses two, then its science will be compromised, and it's one step away from the end of the Hubble Space Telescope.
Right, the next question is from Tom, who is on live with us, regarding the current theory of dark matter. Does dark matter attract or repel baryonic matter? Does dark matter repel or attract itself? And if any of these are true, doesn't this mean that Newton's laws of gravitation are incorrect?
So the best we can say is that dark matter does experience gravity. So let's imagine that it doesn't repel anything. It doesn't have the repulsing property that dark energy has. So dark matter is really quite different in that regard. So dark matter is a gravitational component of the universe, and as such it exerts attraction. And as such, it exerts attraction on baryonic or normal material, protons, neutrons, electrons, and itself. So that's the first part of the answer to the question. Dark matter does not repel, it does attract, and it attracts both itself or other entities like it and normal baryons. What happens then is more complicated because it sort of starts to depend on what the dark matter particle is, assuming it's a fundamental particle. If it's a fundamental particle traveling at the speed of light, perhaps like a neutrino. We know neutrinos have mass because of the oscillations, for which a Nobel Prize was just awarded a few weeks ago. But we don't know what the mass of the neutrino is. However, indirect measurements indicate it's not sufficient to be dark matter. So dark matter is not neutrinos, but neutrinos are illustrative because they're a particle that interacts very weakly, like dark matter, that has mass, like dark matter, and that travels at nearly the speed of light, which may be dark matter. But dark matter also may be a massive particle that doesn't travel at the speed of light. And so how dark matter interacts with normal matter and itself depends on the nature of the particle. And that is the distinction in astrophysics between cold dark matter and hot dark matter. Cold dark matter was dark matter that was subrelativistic at the time the particles were released from the microwave radiation, and hot dark matter would be like a neutrino that's relativistic at the time the particle is released from interacting with radiation. So we simply don't know, and that means there's uncertainty in the models of the universe. There's uncertainty in the simulations, so we have to make assumptions about how dark matter behaves. It has gravity, and there's a certain amount of it, so it has a certain total amount of gravity, but its microscopic interactions will be uncertain until we know what the particle is.
Okay. Next question is, in your Essential Astronomy class, there was a slide that mentioned magnetars. Can you please discuss its unique properties?
Yeah, magnetars are an exciting class of star. They're related to supernovae. When stars, as they collapse, as they reach the end states of their lives, they conserve their magnetic field. So the magnetic field of the sun is essentially trapped in the plasma by the fact that the sun is a gravitationally bound object. And as the sun collapses late in its life, or any star collapses, that magnetic field is essentially squeezed. And so in collapsed end states of stars, the magnetic field is hugely amplified compared to the early stages of stars when the star is much more diffuse and low density. And a magnetar is just a very extreme version of this end state. A magnetar is a very massive star, actually possibly 20, 50, 100 solar masses for almost the most massive stars we know about. Now those stars will die as supernovae, and they will leave behind neutron stars and black holes, depending on the mass of the remnant. And because they are large stars, they as normal stars, they entrain a strong magnetic field. And because they collapse by a very large factor of their magnetic field, becomes incredibly strong. So, and these events are called hypernovae. They're even more strong than a normal supernova. So these are collapsed end states of stars which trap fantastic magnetic fields. How big? Well, refrigerator magnet is about a Gauss. Earth's magnetic field is about 100 Gauss. A neutron star, something like 10 billion Gauss. And the most extreme neutron stars, maybe a trillion Gauss. A magnetar is 1,000 trillion Gauss. That's 10 to the 15 Gauss. That's the largest magnetic field we know of in nature. And so these are pretty amazing objects. And we don't know very many of them. And we don't really know a lot of details about their physical state, but they're obviously very interesting.
Okay, the next question is from Sana, who's on live with us now. What is the speed of causality and how is it related to the speed of light?
Yeah, it's a very good question because, of course, it's a premise of not just of astronomy, but of science that causality operates, which is, and the simplest way to frame causality is to say the idea that events have causes, that things don't happen for no reason. That's almost a philosophical statement about science, about the rationality of science. If events didn't have causes, if things didn't happen for a reason that you could identify, it would really be hard to operate as a scientist. It would be hard to do science. So if events have causes, then we have to be able to trace the causes. And if events have causes, those causes must propagate in a certain way. And relativity, special relativity, implies that the medium, the mechanism for the functioning of causality in the universe is limited by the speed of light, because that's the fastest signal propagation. So if you want an event to happen and it has a physical cause, then according to special relativity, it should only propagate at the speed of light. Now that presumption extends to gravity. In the particle physics version of gravity, there's a graviton, a spin 2 fundamental particle, not yet observed, that carries the force of gravity, and the graviton propagates at the speed of light. No one has ever been able to test, actually, the propagation of gravity at the speed of light. That's an untested presumption of physics. And you can see how hard that is, because somehow you have to be able to turn gravity on and off, which means you have to have mass that goes away or suddenly appears so as to see the signature of gravity propagating through space. So the first order answer to your question is that causality as a backdrop assumption of science and astrophysics is an essential ingredient, because if it didn't exist, then there would be chaos. Events wouldn't have causes, or the events could precede their causes, which would be pretty weird. And then in the modern standard physics, that presumption is that the causality is propagating at the speed of light. But big problem comes from quantum theory. We recently celebrated the 50th anniversary of probably one of the most famous papers in physics. They called the Bell inequality. John Bell was a physicist. I think he was an electrical engineer working at CERN on magnet physics. And he wrote this incredibly important and influential paper 50 years ago that showed that, in short terms, I don't want to take too long with this answer, that physics is non-local. So Bell's inequality is the basis for understanding quantum entanglement, action at a distance, which Einstein called spooky and hated, and a profound problem or conundrum at the heart of quantum theory. And the gist of it is that physics is non-local, which is when you see quantum entanglement experiments, and they're reported in the press occasionally in magazines like Physics Today every year or so, those are experiments where signals appear to be propagating instantly because you have coherent events where if you alter the state of one particle in a shared state, then instantaneously the other shared state at some distance away changes, violating the theory of relativity, in fact. That is very hard to explain. That has to be instant propagation of an event and a cause. So quantum physics is presenting us with a huge puzzle, because it's saying that physics is non-local. That's what Bell's theorem says as a proof, basically, and what laboratory physics is telling us anytime we investigate it. And yet we don't know the mechanism by which these, what I will use Einstein's phrase, spooky action at a distance. He hated it. He didn't understand it. He puzzled over it the last 20 years of his life, but it appears to be real in the universe. We measure it in the lab. And so it throws a whole big wrinkle into the whole notion of causality, because now you have events happening instantaneously with their causes across large distances. Entanglement, incidentally, has now been demonstrated over distances of thousands of kilometers, not just across the lab.
All right, the next question is from someone over email, and I'm going to kind of bump it up because it's topical. And Laura writes, I recently read in a couple of articles, one was an Italian newspaper, that Kepler has detected a star, KIC 846285, with unusual behavior. Can you talk about some of the possible causes? And this is the exoplanet, or this is a star that may have an exoplanet or comets, but people are talking about a possible megastructure, like a Dyson sphere, orbiting around it. So what are some of the possible?
I haven't read the research paper that's based on, so because it's bubbling around, and the research result doesn't speculate about that. It is actually, it's hard to diagnose more than the size. I mean, Kepler is just measuring transits, so the only information Kepler can get is essentially the size of the transiting exoplanet compared to its parent star. But Kepler data, of course, just show you if there's anything near the planet, because you can look for that transit dip and then other dips. For instance, that's how we're trying to look for exomoons. So it's very possible in principle to use Kepler data to look for moons around planets by another little tiny blip alongside the main transit dip. That's sort of beyond the capability, but that's in the realm of the kind of phenomena that's been reported in this news story. It's an other kind of signature that appears to be much more fleeting and therefore physically smaller than a planet or a moon. And so it's presumably some material object that's dimming the star by a very small amount. And the question is, what is it? And the answer is, unfortunately, with that limited information, you simply don't know. So people are, when they find these unexplained signatures in Kepler data that are not just the straight old planet dip that we're familiar with and have seen thousands of times, then speculation really ramps up. So as well as I understand it, it's a case where more information is needed before we can get excited. A Dyson sphere, since that was alluded to, is an entity created by a civilization where they are trying to harness their star's energy more efficiently than we do. The Earth intercepts about 1/1000th of the sun's light at this distance. If we were a highly technological civilization, we could build a sphere, essentially think of solar panels on a sphere around the sun, capturing much more than 1/1000th of the energy. So that would be a signature of a technological civilization. So that's obviously very exciting, should that exist. But I think there's no indication yet that we have any kind of discovery at that level. But it's obviously an interesting question.
All right, the next question is actually about what are neutrino stars. But I figured this would also be a good opportunity to talk about the recent Nobel Prize about neutrinos and explaining the importance of that.
Neutrino
research.
Stars as opposed to neutron stars? Is that the question?
I think they may be mixing up the term neutron stars, but
okay, well, we can talk about
since
neutrinos.
they talked about neutrinos,
right.
that I thought that might be.
Yeah, there is no term that I'm aware of neutrino star, but stars, of course, emit neutrinos as part of their nuclear reactions. So yes, the Nobel Prize discovery, if it were not asked as an actual question, is something I should comment on because it's a very exciting result. And it's a profound part of standard physics that was put in place by these researchers some years ago. There was a puzzle in astronomy going back to 1964, early 60s, where Ray Davis, a famous physicist, built a detector in a mine, in the Homestead mine, made of basically cleaning fluid, looking for neutrinos from the sun, because it's known that out of the nuclear reactions that turn hydrogen to helium, a neutrino should be released from each nuclear reaction. So that means a huge number of neutrinos coming from the sun is of the same order as the number of photons. Those pass through the Earth essentially as if it isn't there, but if you have big enough liquid detector, you should detect rare interactions. Right from the start of his experiment, Ray Davis detected about 1/3 of the number of neutrinos from the sun that theory predicted. Became a huge puzzle. He was dissed in the physics community as not being a good experimenter. That was really unfair to him because it turned out he got it right. He was ahead of the time and the only person able to do that experiment for many years. Eventually, other experiments came online and saw the same thing. One of the Nobel Prize winners was the lead investigator of the Kamiokande experiment in Japan. It's another deep mine experiment shielded from cosmic rays. That's why you go down a mine. Liquid detector looking for neutrinos, and the Kamiokande detector, unlike the original detector, had a lot of energy discrimination. And what people were also looking at is the distinction between the three flavors of neutrinos. In nature, there are three generations of particles. There are three pairs of quarks of different masses. There's up, down, strange, charm, and truth and beauty. And these have different mass ranges. And there are also three generations of neutrinos. The electron neutrino, which is the standard one that we think comes from solar fusion. The muon neutrino, which is more massive, and the tau neutrino, more massive still. And it's still a puzzle in high-energy physics why there are three generations of these particles. What the Nobel Prize was awarded for was the remarkable discovery that these different flavors of neutrino turn from one to another. They oscillate. That's the technical term for a neutrino when it changes from an electron neutrino to a tau neutrino to a muon neutrino. And they literally can change while they're in the sun. They can actually, flip from one to another in the sun. And that neatly explains the Ray Davis result back from 50 years ago. He was detecting 1/3 of the expected number of neutrinos from the sun because he was only sensitive to one of the three flavors. And the neutrinos were oscillating between the three flavors, and he was not able to detect the other two, so he detected 1/3 of the expected flux. So he was right all the way along. The more sophisticated detectors later on were able to demonstrate that neutrinos do oscillate, that these three flavors of neutrinos oscillate or convert from one to another, and that's what the Nobel Prize was given for. Because that discovery demonstrates that standard particle physics is incomplete, because in standard particle physics, neutrino is massless. If neutrinos oscillate, then for various technical reasons, they must have mass. Unfortunately, this is a slight frustration of this kind of physics. The oscillation itself, converting one neutrino to another, doesn't tell you what the absolute mass of either one is. It just sort of essentially tells you what the difference in the mass between the different flavors is. So while the difference in flavors of the three types of neutrino has been measured through these experiments, the absolute mass in electron volts of any one of them has not been measured. So we're still needing that critical piece of information.
All right, and we have lots more questions, but we really need to wrap up and go. So we will try and get to some of these questions, these extra questions, during our next live session.
Okay, and we'll try and get our next session relatively soon, maybe next week. I think we can up the frequency a little bit. So thanks for your great questions today. Again, everything from planets to cosmology. I like the range, and we'll be back again soon. Thank you. Bye.